So we saw yesterday how we generalize, how we can look at Riemann integration in various ways, and thereby look how they could be generalized. And all of them boiled down to the question of generalize the notion of length. Length of the interval to some quantification of the set. An arbitrary set. This is the general goal. Whether we succeed or not, that's a different bargain. That's the question it leads to, whether we can do this. Okay, so once again I will list. So what is length? So length L is the map from the collection of all intervals to the extended real number system. So E is the collection of so there are several things, there are several ways that one approaches these things, and I am fudging a few things because I want to plow through to the main thing quicker. Okay, certain things I will fudge. So the length therefore is something that associates with each interval a real number such that it's a non-negative part. I will write all the properties. As I said again and again, some of them will be redundant, but still I will write. For every interval, the length is positive, and if I1, In are all intervals and are disjoint, and union Ij, j equal to 1 to n, is also an interval. So we have a sequence, finite number of intervals which are disjoint, whose union is also an interval. Then the sum of the lengths is equal to the length of the union. This is called the finite additivity property of S. Okay. This is not very difficult to see. Okay. A consequence of this, it's countable additivity, is little not very well to see, but I'll just take that. Okay. Suppose I is contained in J, then clearly the length of I is I and J, phi and J are in E, then I is contained in J, the length of I. So the length is a monotone function in that. So this is called the monotonicity of length. It maintains the order. The set order is a subset of, and the length is to match the mapped order. So the order before mapping is maintained after mapping also on this side. Okay, so that's called the monotonicity property of the length. And the next one which I said was somewhat non-trivial is the countable additivity property. I'll discuss this a little later. Ij, a sequence of intervals mutually disjoint, pairwise disjoint. So there is a sequence of disjoint intervals and I equal to union j. The union is also an interval, then the length of the sum is equal to length of I, which is the length of the union, which is the sum of the intervals. These are the basic properties of the length of an interval. Okay. Now, when we say we want to generalize this, we would like to push as many of these good properties as possible. We would like to have these properties. Okay, preserved. Nice properties. Because these are all natural properties. Now, when you are measuring things, the one is contained in the other, you expect that the smaller one has smaller measurement than the bigger one. So this is smaller, bigger is already there in our mind and sort of does it understand. So these things should be measured. This is pieces put together must give you the whole. That's the general idea of these things. But okay, this is what we call a simple common sense approach. But this is not always common sense approach. That is, in fact, we got stuck up with this idea of the whole is equal to the sum of its parts, which was not all accurate if you do them in an abstract situation. But as far as these sort of measurements, we stuck to it and we got what we want. Right. So now what we do is the following. What is the natural thing to do? What is, but this is, I have to some stage I will go around with Morel and then suddenly I switch over to Lebesgue and so on and so forth. What is the natural thing to do? The first natural thing is, I have this, say a 5 kg weight and a 10 kg weight and a 15 kg weight. And then if I put the 5 and 10 together in a box, I can automatically say the total is 50. So in other words, I take these basic weights, namely the intervals, and I try to put them together. So if a set is made up of intervals, then there is a chance that I can sort of assign a quantification to it. So the first thing we do is, what is made up of intervals? It must be union of intervals. Well, let's be very humble to begin with. Let's not get into infinite unions, arbitrary unions, etc., etc. Let us say finite unions. Okay. So what we do is, suppose a set A is a finite union of disjoint intervals. Say A equal to union J equal to 1 to 4. K intersection IS and P. Okay. Suppose you have a set which is made up of intervals, then there is a natural way of defining the quantification of this, namely add all the pieces together. That's what you wanted anyway, so you could as well take it as a definition. Then we may define the quantification of A, which we'll call it as M of A, measure of A, whatever it is, as the sum of the quantifications of this, but I want the quantifications of this to be retained. I want the quantification of the interval should always be the length, so I can define it to be so if I have a set which is made up of disjoint intervals, then I may define the quantification of A to be all these pieces put together. So, is this a good definition? First of all, let me ask, this is, whenever you say definition, you must say whether it's a good, when you define the thing, you say, I ask the question, is it a good definition? What do you mean by this? Of course, it's a good definition. Looks good. So, what is meant by good? See, the problem here is, there is a slight technical problem. Namely, the definition is dependent on this representation of the set as a union of disjoint set intervals. Suppose a set can be expressed as the union of disjoint intervals in two different ways. That representation will give one value, this representation will give one value, and if they are not equal, you are in soup. Because you don't know how to define the. So, in other words, that is the definition independent of the representation used, representation of A as a disjoint union of intervals. So, in other words, if A equal to union I equal to 1 to n ij also equal to j equal to 1 to n jk, k equal to 1 to n. Jk, the number of intervals here are m, the number of intervals there will be m. These may be I1, I2, In, then will be j1, j2, am. Then, if somebody uses this representation, he will use this as the quantification of A. If somebody uses this representation, he will use this quantification as are these equal. If they are equal, we are in good shape. If they are not equal, they are in bad definition. You are in terrible definition. See, many times, many times, in fact almost every time, when we do vector analysis, we bring in Cartesian coordinates, polar coordinates and prove all the identities and make it look as though it was the Cartesian coordinate which brought that identity. No, the vector identity exists whether you use Cartesian coordinate or any other coordinate system, and most of the time it's almost meant to believe that the XYZ cleverly chosen is what made that work. That was the only way you knew how to get it. But the vector as it is has its own identity. It has nothing to do with the coordinate system which you chose to represent. Whatever vector identity you got is independent of the system of coordinates you chose. So therefore, we have to be very careful. That's an intrinsic property. Is it an intrinsic property of the vector or is it a property of the coordinate system that is chosen? If it is a property of the coordinate system that is chosen, then there is a danger. You have to be very careful in applying it. If it's an intrinsic genetic property of the vector, then it doesn't matter. Wherever you are, you can apply it. So it should be, you should be very careful about what you are doing. Is it dependent on the representation that you use, or is it direct? So it is like the famous comment, not famous comment, the comment that somebody once, giving a lecture, made a comment that he was discussing some fluid flow. So these types of flow follow this equation. He wrote certain equations. I said, no way. Your equations follow that flow. The flow flows. Whether you chose this coordinate system or any other coordinate system and wrote whatever equation, the flow is going on. It is your equation that is modeled on the flow, and it is not the flow that is modeled on this equation. So it is representation independent. It keeps flowing. Okay, so nothing to do with your x, y, z coordinates or the r theta coordinates or where you put your origin, etc., etc. That's just independent of all these things. It lives in its own world. So we have to be very careful. That flow characteristics have nothing to do with the coordinate systems that you choose. It's independent of it. Then only that's what we want to make sure. The representation is only for simple beings like us to understand it. We want to get it into a language which we understand and then try to interpret what's happening there. So therefore, we must make sure that this is independent of the representation that we chose. If not, it's not a good definition. Okay, so let's now look at whether it is true. Okay. Now suppose I had two such representations. Here it is this as well as that, and of course here what is that I am assuming? Ij are disjoint, and similarly Jk are disjoint. So now we have this following situation. Let's look at Jk. Jk is contained in A. Okay. So Jk is contained in A because A is the union of all the Jk's. So Jk is contained in A. And therefore, if I intersect Jk with A, what will I get? Jk itself. Because everything is in A, so everything will come out. So Jk intersection A will be Jk itself. These are some of the simple tricks which will be repeatedly used. Intersection. What is A? I will use that other. I have to now bring the two representations together to interact. So I equal to 1 to m and j equal to 1 to ij. De Morgan's law, I can write this as union j equal to 1 to m jk intersection ij. Okay. Now what is jk? It's an interval. What is ij? It's an interval. What is the intersection of two intervals? It's again an interval. So these are all intervals. Now if I fix a k and just vary the j, what about these various intervals I get? They will all be disjoint because all the ij's are disjoint. So these fellows have nothing in common between themselves. Okay. So these are all disjoint intervals. Now therefore, what should I say? L of jk is equal to L of, okay, let me write first. This is an interval. It's a finite union of disjoint intervals and length is finitely additive. So therefore L of jk will be equal to j equal to 1 to n L of jk intersection ij. Okay? Because length is finitely additive. Please just put all are intervals. Now that's why I brought everything should be brought down to the base level. Okay. Now therefore, summation k equal to 1 to n summation of Ljk will be equal to summation k equal to 1 to n, summation j equal to 1 to n, Ljk intersection.
Doubt. Here you are saying because IJ are disjoint, JK intersection IJ is also disjoint,
Yes.
then you are using that. That's why you are using.
That's right. Otherwise, IJs are disjoint. So this is I1, this is I2, this is I3, this is I4. And you can find in the JK part in this, the JK part in this, the JK, all these parts will also be.
Last but one equation it should be k equal to 1 to m.
K equal to 1 to m. Yeah, you are right, absolutely right. So that's also be k equal to 1 to m. Now reverse the roles of j's and i's, you will get the same thing again. Similarly, summation j equal to 1 to n, Lij is equal to summation j equal to 1 to n, k equal to 1 to m, Lij intersection. Now these being finite sums, you can write them in any order, you are going to get the same answer. Therefore these two are equal. Okay. So it's independent of the representation and hence it's a good definition.
Sir, IJs put together was not interval, right? Like
Pardon me?
IJs
Yes.
put together was not interval.
No.
So,
But each ij is an interval.
Okay.
So look at this jk. Jk is an interval.
No, I got it.
You got it? That's why I put them piece by piece you look at it. Right. Okay. Now you get the idea of what it is. So therefore, first of all it's a good definition. So therefore, we have a reasonable quantification of sets which are.
So, but JK intersection IJ again are not those.
Pardon me?
JK intersection IJs are not intervals that when you put together you get an interval again,
Yeah, that's what
right?
concerning me.
JK is an interval.
JK intersection
IJ
IJ.
is an interval.
Yes. Put together I get an interval JK.
Put together you get. Oh yeah.
That's it. That's why I want JK to be an interval.
Yeah.
JK is an interval which is a union of intervals, union of disjoint intervals, apply finite additivity of the length. Okay. Here, this is interval. These are all intervals. Interval is equal to union of intervals, union of disjoint intervals, finite additivity, and so on and so forth. Okay. Anyway, I mean, you can say something crazy. That's essentially what's happening. Okay. Next. So therefore, we have a reasonable quantification of sets which are unions, disjoint unions of finite number of intervals. Right. Now suppose I did not bother about finite union, disjoint union. I take any union of finite number of intervals. Let A be the collection of all sets that can be expressed as a finite union of intervals. Suppose I take all sets which can be expressed as a finite union of intervals. Now I am not saying finite union of disjoint intervals. I am just saying finite union of intervals. They may not be disjoint also. Now this class, if A, B belongs to A, implies A union B belongs to A. Because A is a finite union of intervals, B is a finite union of intervals, together again it's a finite union of intervals. So there is no problem about it. Secondly, I belongs to I is an interval which It's a finite, one union of itself, single union of itself, and therefore it's a finite union of intervals, so it's also there. So therefore all the intervals are there, all finite unions of intervals are there. This is, suppose you take this, that's also there. It's not, you have to visualize. See, one way is to take a pencil and draw pictures and things like that. Other one is think. Incidentally, there was a very famous statement. The famous the lecture, I don't know whether you all are familiar with that. Famous mathematician was at MIT, Jean-Charles Rota, G.C. Rota. There was a lecture, I remember, in Fourier Institute or something like that in France. There are some very beautiful 4 lectures he gave at that time on various topics. One of them, he makes a statement very nice that modern science, particularly so-called, whenever we say modern science, we mean the Western science, at least according to them. Basically, says that there are 2 paths that they have taken. One is, he calls them as a Baconian, named after the Sir Francis Bacon, and the other one is Descartian, named after Descartes. The Baconian philosophy is go on observing, collecting data, experimenting, what we are doing in the modern so-called way. Collect data, analyze, collect more data, analyze, collect. The Descartian way is just sit and think, which is what, not modern science, which is what perhaps was very common in the Indian context. Just sit and think. Okay. So you can draw this picture, take a lot of examples and say, okay, I am convinced. Just close your eyes and see what's happening and then convince yourself. Okay. So anyway, let me take it for granted. So why am I making fuss about it? The reason for that is, if you had this, then if something can be expressed as a union of intervals, it can also be expressed as a disjoint union of intervals. If you can, how should I say that? So, then make a statement like this. Every A in A can be expressed as a disjoint union of finite number of features. Try to convince yourself of this. Then therefore what happens? The moment it is disjoint union of finite number of intervals, I can quantify them. So therefore, it is not just that I can quantify sets which are finite unions of disjoint intervals. Even if it was a finite union of non-disjoint intervals, you could bring back to this form, I can quantify it. So essentially, this is saying that I can express, this is nothing but saying that it is a finite union of disjoint intervals. So unions, the reason is, how do you do that? This is a famous thing. If you are A1, A2, An, then you can write the union of these Aj's as, first you write B1 as A1, B2 as A2 minus A1, that is where we wanted that 2 to be there. Okay? And then B3 as A3 minus B1 union B2 and go on like that. Then the union of these will be the union of the A's, but these are all disjoint and you are done. And now the fact that this is there, it shows that everything here is finite union. Basically that's what it is.
So can we say this is analogous to Gram-Schmidt orthonormalization?
No, this is not Gram-Schmidt.
No, analogous to Gram-Schmidt orthonormalization.
No, I don't think so. This is not the Gram-Schmidt orthonormalization. It is a plain common sense of getting rid of redundant information step by step. That's all. So the fact that you can write it in different ways as the union of disjoint intervals is, I could have started with A4 first and then looked at A2, then looked at A3. You could have done it in many ways you want, but still what that says is whatever way you do, final sum of that length will be the same. That's what it says. Okay, so therefore, we have this situation. So let me start all over again. So we had this. Maybe I get the length part of it. So let me now start from this end again. I can keep at least moving. So if you have A, which is the collection of all pointed of intervals. So this convenient I'm writing the word disjoint now because every time I can do that. Okay, then we have a quantification. M into R star such that 1 why is it positive? Because it's sum of interval lengths. Its interval length is non-negative, so it has to be non-negative. Many of these things I keep repeating, and I just write that. Many of them follow from the others. Okay. If I is an interval, what is the difference between MA and LI? They are both same because I can be expressed as I, as a single union, disjoint, and therefore the MA I is the same as LI. So MI is the same as L. In other words, this quantification does not destroy the quantification you already had on known things, namely the interval. So in that sense, it is uplifting our knowledge. We have just pulled ourselves up. Okay. MI is equal to 3. If A1, A2, An are in A and Aj are all disjoint. Now let's see what happens. Let me write here. So, if you look at Aj is in A. So Aj can be expressed as a finite union of disjoint intervals, because anything there can be always brought back to disjoint intervals. So these are all disjoint intervals. Anything in A can be written as a disjoint union of intervals. Then, therefore, if I look at A equal to union J equal to 1 to n Aj, that will be equal to union J equal to 1 to n Ijk. And because these fellows are all disjoint, these fellows will all be disjoint, because what appears in the construction of Aj will not appear in the construction of Ak, Al at all, because they have nothing to do with each other. So now these are all disjoint intervals, finite, finite. So A is a finite union of disjoint intervals. So that says MA is equal to summation J equal to 1 to n, summation K equal to 1 to n. What should I write? K equal to 1 to Rj, Lj. But what is this? So Maj by definition is equal to whenever you express a set as a finite union of disjoint intervals, the quantification is the sum of the intervals. So this is precisely Maj. So therefore, what this result says is, this says M of the union J equal to 1 to n Aj is equal to summation J equal to 1 to n Aj. So this M retains the finite additivity property. So M is finitely additive. sequence of sets in A.
Why did you have to break it down like this in this case?
Why do we have to break it down? Which one?
In that case, yeah.
Otherwise, how do you prove?
The union has to be interval.
We have to bring one. We know only finite additivity in the interval case. We have to now prove the finite additivity in the new case. Okay. The new case additivity is implied by the old. So in other words, really this is a genetic property. The way we have defined, the information of finite additivity is passed on, the information of non-negativity is passed on, and those fellows who are reborn again keep their identity completely. And now we will see that even all disjoint. Now what will be the difference in the same argument? Except now I will have this, again this. Now can I write this? I can still write this because these are all intervals. These are all disjoint intervals, a countable number of disjoint intervals, and what? I'm in trouble. Right? How do I write that? NMI is equal to this. Only when I have finite number of intervals I can write all this. So that requires a proof. Okay? It is still true. The proof. M of union J. So that's one thing which requires a little bit of proof. It's not difficult. We'll hold it for a moment. What I want to say is that if this whole fundamental properties that I listed for intervals gets lifted up. We are now one level higher. We are now learning only the intervals. First standard is over, now we have come to second standard. All this finite union of intervals we are able to handle. Okay. But there used to be, I think, I don't know, there is still a rule. Don't give addition of more than one digit number to first standard. I don't know why this don't give. Give to fellows who can handle it. Why you make a rule, don't give at all. So I remember long back there was a discussion in the Senate in the institute that nobody should be allowed to take more than 16 courses. Then it went on for 1 hour, 1.5 hours. Then I lost my patience. I got up and said, I cannot think of any educational institution which will put a bar on a person's learning. You can say that minimum you should have 16 courses. How can you say that you should not take more than, and you should never take more than 16 courses? If somebody is capable, why do you prevent it? You fix your minimum requirements. If somebody surpasses it, be happy with it. So, in that sense, don't say that only intervals you deal with. We have lifted ourselves. We have gone up to finite number of intervals at least. Okay, slightly higher level we are able to handle. Okay, so that is one thing which requires little English proof. We will come back to this and investigate all the other intricacies involved with it a little later. But that's one thing which I take for granted at the moment. So one more thing which I want to observe is the following. The monotonicity I haven't looked at yet. But then it follows, suppose AB are in A and A is contained in B. Then I can write B, very good, this is B and A is a part of it. Okay? A is contained in B. Then I can write B as A union B minus A. Right? Disjoint. Now what is this? So I can write that B1 union B2. This is B1, this is B2. B1, B2 disjoint. They are in A. Why? This fellow is in A. and we showed that the two fellows are in A, the difference is in A. That, I mean, we at least claim that. So therefore, we have B as B1 union B2. Now therefore, by the finite additivity, when you have two disjoint fellows in A, M of the union is there. So therefore, M of A, which is M of B1 union B2, is M of B1 plus M of B2. Now, M of anything is non-negative. Therefore, M of B2 is non-negative. So we are adding something to M of B1. So therefore, it is greater than or equal to M of B1 which is equal to M of. Therefore, I'm sorry. This is M of B. So M of B is greater than or equal to. Here M of A is less than or equal to M of B. Now, there is a slight thing that I want to point out here. From here, we can't write M of B1 is equal to M of B. See, this is, we can't write within inverted commas. Question mark. This is, now let me write it explicitly. This is M of A plus M of B minus A. This implies that M of A is equal, or M of B minus A is equal to M of B minus M of A. Does it or does it not? M of B is equal to M of A plus M of B minus A. Does it imply M of B minus A is equal to M of B minus M of B? Yes or no? All this has done is, he has taken it to that side. Okay? So therefore, M of B minus A is equal to M of B minus M of A. Now what is meant by it has taken it to that side? See? I have subtracted BA from both sides. That's all. Okay. Now MA from both sides. The problem is the following. We may get into such terrible situations where both are infinity. Right? So then the problem is, what is infinity minus infinity? MB may be an infinite measure, MA may have infinite measure, and what is meant by infinity minus infinity? Now we write this very happily in probability theory. That's because there we have all finite measures. So it's not that probability one is the important thing there, that everything has finite measure is important there. So if you have finite measure, this can be done. But when you are dealing with infinite measures, you got to be very careful. You sort of pushing things back and forth from one side of the equation to the other side, involving measures, you got to be very, very careful. Okay. So this is in general we won't write it that way. So that's why we write MB is great. Only we can write MA is less than or equal to MB. It could be equal. And this is where, in a sense.
So, but in this case, will be telling something like infinity is less than infinity.
Huh?
We both have infinite measure.
No, the problem is, I am not saying both are both A and B could be infinite sets. See, for example, you take B to be minus infinity to infinity, the entire real line. What is the measure of B? Infinity. And you take A to be 0 to infinity. What is the measure of A? A is strictly contained in B, but still, so therefore, you already see when you are dealing with the infinities, Euclid has to bite the dust. The part is always smaller than the whole is what his claim was. But that the part is smaller than the whole is not correct. When you are dealing with infinity, Euclid goes haywire. And that's where I think Cantor really made people sit up and look at all the things that he did and were very unhappy with what he was doing. He says, what all kinds of crazy things. How can the part be equal to the whole? It's 13, almost like thousands of centuries of what thousands of years of what we have learned, this fellow is trying to kill. What is going on here? So, but it happens that in the world of infinity, things are very dangerous. Okay? Not very dangerous. Very dangerous if you assume that the same thing that happened in the finite world happens in the infinite world also. So, therefore, when you are dealing with infinite measure, you got to be very, very careful. You don't say infinity minus infinity. It doesn't make sense. That's the situation you may have in a situation like this. Okay. So therefore, we have now made some progress from the length of intervals to those made up of a finite number of pieces of intervals. That's not a big deal, okay? I mean, that's a simple common sense. And the way you do it, if you do it carefully, everything is there. Now the question is, what do you do? Well, you could go further. Namely, you started with intervals, put finite number of intervals and got that new set. Now you can start with this new knowledge and start thinking of finite number of pieces put together from this. But when you put finite number of pieces put together from A, will again give you only A. So nothing is going to come out. So what Bayer and Borer started doing was put infinite number of them together. Okay, that's the process by which they went about constructing the measures. So start putting infinite number of A sets and see what happens. It's the same thing as essentially saying put infinite number of intervals that put together and see what happens. We put an infinite number of disjoint intervals, define the measure of that to be the sum of the infinite series. If it converges, it's fine. Otherwise, they say this is infinity. The measure is infinite. And they proceeded going on putting infinites and things like that. But what Lebesgue did was the following. Essentially, what Lebesgue did was, now let's backtrack and say that anyway, I will do it, backtrack with the intervals again. If I want to take that path, then this intermediate path, basically what it said was, first make sure it works in finite and then go to infinite. So now I will directly go to infinite. Start with intervals, put countable unions. The countable could be finite or infinite. What Lebesgue did was, instead of that, let me take an arbitrary set and estimate its whatever meaningful quantification that I can give. What does it mean? So here is what Lebesgue does. Now first, actually this, what is written in basically now in standard textbooks and Lebesgue, it's not exactly what Lebesgue did. Lebesgue did slightly different, but it all has been now afterwards, look, oh, it could have been put this way, it could have been put that way, it could have been done this way, etc., etc. Okay. Now let me first say what we say, what most of the books would say, what is the Lebesgue so-called outer measure or the estimate. So what you do is the following. First let us do this. Take a set A, which is in R. Then I want to estimate the space occupied by that. See, what is an interval length? It is some kind of quantification of the space occupied by the points in that set. So that's what Lebesgue would call the content of that set. Okay. So we would like to estimate the space occupied by the points in that set. What do we mean by that? So how do I estimate? I can estimate only through the known measures. The known thing is only the length of an interval. So what I do is, look at, now I'll write a sequence of intervals, or a countable collection of intervals. Now everybody writes open intervals. Previously, some earlier books would have semi-closed. All these mess will be there. Okay, but let me now write open intervals. One advantage is immediately that you bring in the notion of open, then there is this idea of extending to metric spaces, etc., comes into the picture. look at a countable collection of open intervals IN such that I don't even bother whether it is disjoint or whatever it is. Just do carefree. See, the first thing is when somebody gives, what will be the weight? You must be able to make an andaj order of estimate, 10 kgs or 20 kgs, 30 kgs. You cannot say one fellow says 20 kgs, another fellow says 20 grams. That means something is wrong in the perception. Okay. So, but we are now doing it that way. Doesn't matter, we'll do it as this thing. What it is, suppose, for example, if you go to a shop, okay, you have a bag full of rice and you want to find the weight of that rice. You give it, and if that person is a fairly elderly man who has been sitting in that shop, whom you have seen him from your childhood, the first 2 or 3 weights that you will put there will bring you very close to the bag weight. Such his perception is so good. But if you go to the same shop with some young boy who has just been employed, he'll put something, it'll die, it'll go up, then another will remove it, like that. He'll have, because it's an experience. So we behave like that now, we don't care. Simply take all the weights put together. What I am doing is, so that this balance comes down, it's more than what it is. Okay? And therefore, if I now take each one of the weights I have put and add them all, that will be a simple overestimate of the weight of A. So therefore, look at summation j equal to 1 to infinity Lij or n equal to 1 to infinity Lij is probably a gross overestimate of the content which
So is it required to take the collection to be infinite and you put summations?
No, I should put only summation only and no. Well, if it is finite, take the remaining fellows as empty, okay, in that sense. But anyway, it to be said, let me put it, it's not necessary that they be infinite. Okay. I'll put just over n. Because now you will see. If they are finite, or if you want all of them to be written as infinite series, then think if it's only a finite cover, then take the remaining fellows as empty. An empty set can be thought of as the open interval 0, 0. Right? So think of an empty set as an open or A or any A. Right. So therefore this is a gross overestimate, probably a gross over, maybe not, I don't know, but I've been very lucky to have got it. It depends on the experience you have. So what we do therefore is, we are overestimating the content of A, then let us take the best overestimate. What is meant by the best overestimate? Take all the possible overestimates and take the smallest, which is the infimum. So to bring that language correctly, what we will do is, a collection, a countable, will introduce some terminology. Collection of open intervals. Let me call it a CO, A, I1, I2, IN, etc. is called an open interval cover for A if union N IN contains it. Let Q C naught A be equal to summation So this quantification is an estimate based on this cover. So let QC naught A is overestimate of the content. So let CA be the collection of all open interval covers. Open interval covers. This is one. Let every boy weigh. Every boy puts some weights and overweight. Okay. So let that be the collection of all. So for each one, for each C naught A which belongs to CA. So CA is the collection of open interval covers. This is one open interval cover. Okay. Q C naught A gives an overestimate of content. Take the best overestimate. That is infimum QC naught A when C naught A varies over. Why I put C0 but anyway, CA would have been enough. Okay, so they take the best overestimate. Is that clear? Any question about this step?
What is the lower bound for this? If you take this infimum?
It will be positive because you are taking, it is bounded below
Yeah.
because it is 0 is a lower bound. Therefore, there will be an infimum. I don't know what it is. Certainly, infimum is well defined and it's a finite quantity. I mean, it cannot be negative quantity. It could be still be plus infinity. Okay. So, infimum is well defined. Okay, let me possibly write that. QC0A gives a QC0A is greater than or equal to 0. Okay. Therefore, infimum is well defined. No problem about that. Yeah.
So QC0 will be defined as length of IA.
Sum of the length of the edge.
Should that be M or L? Because now this can be nothing to say that IA is a disjoint.
I didn't say.
But
It's just a overestimation.
okay.
You put 2 kg weights 10 times, I don't care.
So even if these ions are intersecting, it will be.
It will gross over, that's why I said it will be a gross overestimate. Same thing may be counted again and again. Okay, that's what I said, the gross overestimate. What we do in assessing our cricket players, once he scores 50, we go on talking about him for the next 10 years even if he scores a 0. That 150 has been grossly overestimated. Again and again we talk only about that. We don't talk about the number of zeros he scored subsequently. It's exactly that. Okay. Right. So, or we win once. Oh, you keep talking, Gavaskar keeps talking about the 1971 in Oval Test victory. Because we didn't win anything after that. We have to go on talking about that only. So, gross over talking about that. So, you can see that I think for the rest of my lifetime I will hear about this last week's victory. Then we play a test match in South Africa or elsewhere. Anyway, at least in my lifetime, I had opportunities to look at some victories. It was not so in my early days. Annual days we used to do every test match. By the way, okay, anyway, let's get out of that. Okay. So therefore, this infimum is well defined quantity. So for every set A, we have this. Now we would like to take this as one quantification of A. Now we will call this, there is a notation for this, we will call this M star A and it's called the outer measure, outer Lebesgue measure of A. Why is it called outer? Because I am trying to approximate the set from outside. Something bigger than A only I start with and then squeeze it. So that's why it's called outer measure. You can ask whether there is something inner measure. Yes, Lebesgue did that also. The reason is we are allowing now for infinite sets. Now to suppose I have minus infinity, infinity. I have to look at from inside and then go on taking inner estimates and then take the best of the underestimates, which is the supreme. Okay, these sort of things we will have to do. But let's stick to one way only, outer this. Even whether this works or not, then we have to worry about the inner, etc., etc. Okay, so now we have this outer measure. Well, first of all, one thing I was sloppy was, given any set, there is at least one such cover. We should not be taking infimum over an vacuous set. Because if there are no such cover, then where are we taking infimum over? The C may be empty. Okay, therefore we are taking infimum over the vacuous set to make sure that we have at least one such cover. What is that cover? It is R. So that's not a vacuous cover. Take one thing, R covers A. So okay, the infinity, that's anybody's great achievement. Infinity is always a great grossest overestimate you can make for anything. Nothing is more than plus infinity. So take plus infinity as one of the best overestimates. Take R. So this is not a non-vacuous infimum. It is not a vacuous infimum. It's a non-vacuous infimum. Okay. What should be? Therefore, we have a quantification of every subset of what? Take any set here, we have a quantification, namely the outer measure. Okay, so sudden excitement. It will be very nice if 1 MA greater than or equal to 0 for every A in R. It is nice. Because you are taking infimum of non-negative quantity, so it has to be non-negative. 2. Of course, M5 is 0. It's true. Okay. Why is it true? Phi can be covered by minus 1 by n plus 1 by n. So the length cannot be more than 2 by n, the measure quantity. Infimum of as n varies will be 0. Okay, so M5 is 0. Then 3. The length of I must be equal to this new measure. See, every time when you go raise your bar, you don't want to lose your old friends. My old friends were the intervals, they already had a quantification. I don't want to give a newer label to them. The old label must coincide with the new label, and that's also, these all have to be verified. So these two are obvious. So this is a question mark. 4. A1, A2, An, finite, disjoint, finite number of disjoint subsets of R must imply M star of Uj equal to 1 to n Aj equal to. So that's another question mark. Well, that is true. Finite additivity is true or not. Next question is A1, A2 sequence of disjoint sets. Implies M star of union n An equal to summation M star An. That's another question mark. This is it. Whether it is countably additive. The last question we have is A contained in B come on and answer. That's a question. Okay. So now, if we had this, There is no problem about finite additive. Countable additive, finite additive, put the remaining fellows as empty set and that's good. So this is not really a big ask. We don't have to worry about it at all if we have this. And if we have finite additivity, this is obvious, that's what we saw. Which is finite additivity, we use that MB is equal to MA plus MB minus A. So that's all. So the main question is this. Now it turns out, so therefore, is M star an extension of M. That is, if M star I equal to Li or Li. That is what is meant by extension. The old place it remains the same, in the newer place it gives you a new meaning. 2 is M star counter period. These are two questions that we have to ask. If the answer to both these questions is yes, nothing like that. We have quantified every set under the sun on the real line, and that quantification is an extension of the length, and it preserves all the basic characteristics of the length. Total is equal to the sum of its parts, monotone, part is less than or equal to this thing, everything is like that, then we have an ideal situation. Unfortunately, this is true. Okay? So therefore, the problem is we can show that yes is the answer for 1, and no, in general no. Is the answer to the question. So, what do we do? So, we started off with a great hope, and suddenly we find that we are in trouble. We are not made a real good progress. Well, there are, again here, there are various ways of looking at it, and but I look at it in the sand, what is normally done in percentage exposed. The situation therefore is, what do we do? We give up hope, or say, backtrack and say, look, I've been over-ambitious. From the intervals, I simply wanted to zoom to all subsets, and that perhaps is not my distribution. So it's like the way we start our PhD thesis. I want to prove Riemann hypothesis is my ambition, and eventually I end up proving something which is totally disconnected with Riemann hypothesis, because that's what I could prove. It's something like that. So we say, look, I've been over ambitious, let me backtrack. What I say is, this seems to be still reasonable. This seems to be still reasonable, but it's not satisfying this property, because there are some cases where we are unable, actually we are unable to show that we are able to show when it is less than or equal to, and we will be able to show that sometimes it is not equal to. It's a hard construction involving non-measurable sets and so on and so forth. So what one does is the following. Well, let's not give up this completely, and let's not stick to all the sets requirement at the same time. Somewhere we have to come. So let's say we will not consider all sets. Suppose a restricted collection of sets on which I do this, and for that restricted collection of sets this is valid. That is, I want to have, suppose B is a restricted collection of subsets of R. That means what? Not all of 2 to the power of R, not all the subsets, but some proper subset, and we'll simply say is a collection, a proper subcollection of subsets of R, and M star is the restriction of, we look at M star restricted to B. Only for those sets we do this overestimating business and all, and call it MB. You look at MB. Will MB become? What do you mean by that? All these properties must be set, particularly this countable additivity will it now come to this. You won't allow all possible sets, but only from some restricted collection. Now, whenever we do that, recollect, we wanted to always have this collection to be a sigma algebra, because we want to do all the set theoretic operations within themselves. Okay. So suppose B is a proper subcollection, proper sigma algebra of subset of R, and look at this, will it be? The answer is yes. The first situation is take B to be the Borel sequence. That's what Borel did. What he did was he did it other way around. Instead of taking finite unions, look at infinite disjoint unions and do it. That route will lead to the same route of restricting to this to the Borel sets. Okay. That's called the Borel measure. We get then the Borel measure. The second, what Lebesgue found was the following. There is a bigger, there exists a sigma algebra M of subsets R such that B is strictly smaller than M. The Borel sigma algebra is smaller than this sigma algebra, but this is definitely smaller than set of all subsets of R. Somewhere in between. I do better than Borel, but I have not done the rest. Okay? And this is called the Lebesgue measurable sets, and M star restricted to this is called the Lebesgue measure. M star restricted to M is called, I will call it the Borel measure, called the Lebesgue measure. Yes? And now Lebesgue says, I can do integration with this. I can now partition any given measurable set. Anything in this is called a measurable set, Lebesgue measurable set. Now, take this, partition it, take constant functions on it, approximate by simple functions, do all that integration I wanted to do, I will describe that, and I get this so-called Lebesgue integral. And because of this, essentially what happens is, the Borel Lebesgue measure is an extension of the Borel measure. Whatever happened will happen here and something more will happen. So all the Riemann integrals will come through, but something more will get integrated. And that's what the Lebesgue thesis was. Okay. So now this is the part which we will start looking at. I'll start looking at again from that estimate, the infimum part of it more carefully. And then look at this fundamental question and show that the answer to this question is no. In general, we can only prove less than or equal to, and later we will show that there is a situation where the strict less than will come into the picture, and then look at this Lebesgue measure. Okay, and That's the plan of action for the next performance. So basically what the idea is, now the abstract construction of measure, I mean just a few words. What it says is you have some basic weights. As long as you have all the necessary properties in those basic weights, like finite additivity, countable additivity, monotonicity, etc. are there in that, you can do always this overestimating business and construct the outer measure. And the outer measure in general will not be countably additive. You have to restrict it. In fact, the way we restrict it is a very peculiar definition which came through Carrot theory. Lebesgue's idea was, the way he did it was different, but Carrot theory gave a different definition of measurability, which allowed us to go for abstract situations also. So then we will see that the same thing can be construed. You can come up to this. The answer to question 2 will again be not necessarily. So again we will construct M like this, restricted to M star, restricted to that will be a measure, and therefore we will construct a measure on a sigma algebra. So always you could start with some basic measures, basic sets and quantification of those basic sets which have the fundamental properties that can be lifted up to the sigma algebra by this construction. And this is what is done in probability theory. This is exactly what is done in probability. You have the sample's probability space and you have a random variable, and the random variable induces a measure on the real line, and you do the integration with respect to that measure. Okay, that the so-called distribution function comes into the picture, and why do we do it? Because we could measure intervals on the real line. How could we measure the intervals on the real line? We quantify the interval as the probability that the random variable comes and sits in this interval. Originally only the probability measure was given, and that was given in that sample space. Through that, I am constructing a measure on the real line. How do I construct? My construction is as long as it do tell me what you should do for intervals, I know what to do. The rest of it I know what to do. Same outer measure I will construct, I will do the measurable set, everything else is not to be, just tell me what to do for intervals. Well, the quantification of an interval is the probability, that is the only measure I have, so I go back there. The probability that the random variable lies here. So every random variable is a measure on the real line. And you do all those integrations with respect to that measure. Okay. And that measure is also induced by a function in most of it in general, and that's called the distribution function. And the Lebesgue measure is induced by the simple function fx equal to x. Okay, that's the length of the interval that gives fx equal to x, then the distribution function, whatever you want to call it. Then we get the length interval, but in arbitrary non-decreasing functions defined on the real line, introduce different measures. So that's the basic idea of Lebesgue measure and the abstract construction. Once you understand what is going on in the Lebesgue measure, the abstract measure. So what will happen is, in some of the proofs in the Lebesgue measure construction, we will explicitly use all the properties of the real line that we know. The properties may be algebraic, the properties may be topological, but if we have an abstract set which may not be having any algebraic structure on it, may not be having any topological structure on it, then if you go on copying this step by step, at the step where you used some topological idea on the real line, there you will be stuck there. What do? You put a hypothesis so that place is got nowhere. Okay. So you know exactly where you need what type of hypothesis. Wherever I am stuck here, because the topological idea I cannot carry over, that must be built into the system, in the construction. That's all. Okay. That's how the abstract measures are constructed. The basic idea of constructing the abstract measure is, first learn to quantify very elementary sets like the intervals. Once you have that and quantify it in a proper manner, that is, you have that countable additivity at least at that level, then just lift it to measure construction Then restrict the outer measure to a suitable sigma algebra. That's the general